Okay, Audrey, 1 minute.
I just started the recording and the transcription, so we should be ready to roll.
Okay. All right, let's get started. My name is Torben Grumstrup. I'm filling in for Natalie this week. She's away on leave. And it's my pleasure to introduce Dr. Faraz Hedayati and Dan Gorham. And they're from the Insurance Institute of Business and Home Safety. And they're going to be telling us about their test chamber and its capabilities, and hopefully have a nice discussion afterwards about opportunities for collaboration. So just a reminder, hold your questions till the end and type them up in the chat box, and I'll read them off. And then I think we're ready to go. If you guys want to go ahead and put your screens up, we can get started.
Thanks, Torben. I think Faraz is going to be sharing his screen with our slide deck. And while he's bringing that up, I'll just kind of give some context. Faraz and I are going to kind of split up some of the slides here. We work very closely together on a lot of these projects, and so we do these kinds of presentations. So Faraz will be running them, but we'll both be speaking throughout. So thanks for the opportunity to speak with this group. And as Torben mentioned there, we're happy and very much excited to share some of the previous and ongoing work and capabilities of IBHS, but really looking forward to the discussion with this group, this fire science group, about future opportunities in collaboration, which Faraz and I believe is a really important part, both organizationally, what we do at IBHS, and really the path forward towards addressing some of the mission-oriented things that IBHS does. So with that, Faraz, I don't know if you wanted to get going. Thanks. So we're streaming video over Teams, which is always dangerous, but this is giving you a fly-through of the IBHS Research Center, located in Richburg, South Carolina, just south of Charlotte. And this is a video showing some of the different perils that we look at, including hail, including wildfire, which Faraz and I both work on closely and will be the focus of today's talk. Rain, and particularly wind-driven rain, as we commonly see during hurricanes, but other wind events, and then also high wind. And so again, this can be hurricane or this can be tornado. And so we call these our core 4 perils that IBHS looks at. We look at both residential and commercial. We, in the test facility, which we'll talk more about, we can put a full-size structure. And in this case of a wind test, we blew the roof off and out the back apron. Not exactly what we expected, but is aligned with the stuff that we're capable of doing. And you know, again, hopefully the streaming video was sufficient enough, but just to give you some visual sense of some of the pictures we'll be showing you later. Moving along to our why statement, and again, I maybe could have mentioned this at the top. IBHS, that's the acronym for the Insurance Institute for Business and Home Safety. We're a nonprofit organization. We do receive our funding from the insurance industry, particularly the property insurance industry. Our members include primary carriers as well as the reinsurance carriers. And then those affiliate members, think, you know, companies that support the insurance industry, like Insurance Tech. And really the focus is on property and how they are impacted by severe hazard weather events. Again, going back to the core 4 perils, we primarily look at hurricane type events, wildfire type events, and severe convective storm, which generate the hail. But as a nonprofit organization, although I think all of us can appreciate it, you know, we have a very center why. Our CEO, Roy Wright, probably can go back one, please. our CEO Roy Wright came from the FEMA flood program, and often talks about understanding and focusing on our why, and creating a why statement. And so this is ours right here. Very much focused on severe weather, how it disrupts lives, financially, yes, but also displaces families and can some instances destroy things that have irreplaceable value. And we're focused on the top tier science, which Faraz and I will talk about today from the research team, and really importantly, translating that into useful, actionable, real world impact things, ultimately to avoid the suffering that these hazard events can have. So again, you'll hear this a lot in what Faraz and I talk about and what we do. And this picture here shows you the research campus to hope to give you a physical scale and sense of things. But it's all aimed at trying to better understand the natural hazards at the fundamental level, but also how they impact the built environment. And then, with that research, leveraging that science and turning it into building new as well as retrofitting existing community to be more hazard resistant. So with that, Faraz, on to the next slide, which is the last for me, and then I'll hand it back over to you. We have the 4 core perils here. I think I'm waiting for next slide.
So I'm going to the next slide. Does it update for you or?
No, we're still seeing the why statement.
Okay.
Actually, it does show up. It might not for you, Dan, but I see it.
Okay. Okay, then maybe this is a connection issue on mine. I'm going to turn off my video, hopefully lower the bandwidth. Yeah, looks like I'm lagged behind. So Faraz, I'll finish up here and then rejoin. But again, the 4 perils, and really kind of focusing in on something I mentioned there at the end is translating the science, the research we do into, again, the phrase that we'll use often is the real world impact. And Faraz is going to talk about that, again, particularly for, combining 2 of the hazards, wind and fire. And that has lots of impacts on the real world, from the code and standard side of space to the development of the standard test methods, to providing guidance to homeowners and communities to retrofitting and building new, more resistant to the hazards. So with that, Faraz, I'll hand it over to you to talk about some of the research stuff.
Yeah. Thank you, Dan. So in order to have real world impact, we need 2 parallel avenues of research, in my opinion. One is fundamental research, which I will talk about it shortly. And then there is applied research. How do we take this and make that digestible for public, for our member companies, for legislators, all of those. And these are, again, like parallel avenues. We kind of like separate them. So this video that you see here is from 2016 fire in Canada. Let me see if I can play it. So regarding the risk to structures, we're talking about 2 different things. One is big, tall flames on the left-hand side, which is a risk that a homeowner can take or an insurer can take when they're underwriting. And the other part is the homes on the right-hand side, which are smaller fires, which obviously are embers, fly off and land on a fuel ignited. So if we want to talk about the risk, we need to divide these 2. And what becomes important here is, excuse me, what becomes important here is ember accumulation near the structure. And we need to understand that mechanism to provide recommendations and strategies to fight the embers, right? Go to the next slide. Okay, so I really like to look at embers as smoke, so particles with 0 mass. And the reason is those type of particles, they have no inertia against the wind pattern, right? Wherever the wind goes, the smoke follows. Embers are not like that. They have mass, so they're fighting or actually have inertia when they interact with wind. So what you see here is IBHS test chamber inside, and we have different several ember generators that can create embers with different size. And then we add wind to that. And taking the analogy from smoke, so we see that the inertia of the embers actually change the pattern. Embers do not solely follow wind. So we see different type of embers here. The one that hit the wall and just fall. And you see that glowing line at the base of the wall. That is basically heavier embers. The smaller embers, when they hit the wall, they bounce back. And that's where we see the glowing arc around the structure. And then the heavier embers that land at the base, they stay there for a while, they lose mass, and they are light enough for the wind or the vortices to move them around, and they go back to that glowing arc. And that's what the push and pull that we see there. So two things are important here. One is ember inertia, basically mass, area, its aerodynamic shape. And the other one is the wind. So I want to double click on these two here, and how do we create that wind in the chamber. So wind, if we want to create constant wind, we can have different RPMs to the fans. At the same time, we can read the velocity at a certain distance in front of the fans, and it's a linear curve, right? It's not a curve, a linear line. So we can create that line, and then if we want to create a certain wind speed, we can do it backwards. So we can look at the desired velocity, and then find their RPM, feed the fans with that RPM, and create the wind that we want. So basically, if I want to animate that, a contour volume of air, let's say, leaves the fans, and then we can measure it as it gets closer to, or closer to the probe, at the location of the probe. When we are talking about gusty wind, it's a different animal, right? So we have dRPM dt. So when we ramp up and ramp down the fans, the contour volume that we talk about is not going smooth. So it's like there is a push and pull between the contour volume. So when the contour volume leaves the fan, as we ramp up, the next contour volume pushes it forward, and as we ramp down, it sucks it backward. So it's always like it inherent noise in the measurement. And that's this inherent problem makes it very challenging to create a desired wind history, time history of wind. So, and as simple as a sine wave. If you want to create a sine wave, it's a try and error thing. So with different frequency and amplitude of the sine wave, we can play with the fans to create that. But a real wind is not a sine wave, right? So it is a combination, let's say Fourier transform, combination of these different sine wave to create that desired time history. Another layer of complexity to that is that the fan curve is not a linear thing. So we can go from, let's say, either 200 RPM to 1000 RPM in a quarter of a second. If you want to build on top of that, going from 1000 to 1500 takes more time. And then from that to the maximum fan, which is like at IBHS 1900, 1800 something, takes more time. So all of this makes it very complex to create a desired wind history. Going back to the smoke analogy, we can create different energy at different frequency. And that becomes important when we want to talk about their distribution and ember accumulation near the structures. So this is a energy distribution with normalized frequency. You see like the models, Van Karman and Kaimal, which is like the famous models, and then the measurements that is done by Texas Tech University. And we see that, well, Mother Nature can do it very well. But when we come to the lab, how can we create and put all of those right gust structure at the same time to create the right energy spectrum? And that energy spectrum causes the right distribution of embers. So for constant wind, we could use a deterministic approach, right? So, but for gusty wind, we cannot use that model anymore. We need to go to stochastic models. So I have a two-dimensional plot here. So basically two predictors and one response value. We cannot go more than 3D here. So, and this is like Gaussian process concept that we use to program the fans. I want to like double click on this. I love this technique. So let's say we have a 2D normal distribution, x1 and x2 and p of x1 and x2. So it's normalized, so the mean is 0, and we have the standard distribution of sigma 1 and 2. If I know x1, in our case RPM 1, let's say 300 RPM, and I want to go to another RPM. How can I do that? So if I fix x1 on this curve, I have a probability density function for the next one. So if I have x2 at a higher probability, I can predict it. And if it has a lower probability, I can also predict that. So at the end of the day, I end up with another normal distribution. And we can build on top of this, go to 3D, 4D, and all the way. So at IBHS, we thought that we have, well, fan curves, velocity and its derivatives, temperature, moisture, relative humidity, all of those could be a predictor into our models. So we're talking about the 5-dimensional probability density function. With section 1 or a slice 1, we find the probability density, the 4-dimensional probability density function. We slice that again, and then we get to the final RPM. So with this technique, which is again Gaussian process, we built a model, and then we used Texas Tech University measurement. They have a probe for several years out there. They're just collecting data, and we had access to that data. Once we created that model, we trained that model, we asked the model to recreate TTU measurement. And here is the result. It's pretty close. So we are moving away from matching statistical measurements such as mean, standard deviation, and we are matching time history. And in my opinion, it becomes very important when we want to look at embers as particles that interact with wind. We want to pose the right force on them, and for that we need the right gas structure. So you see that we miss the peaks and some of the valleys, but for the most part, we can create that. And the reason for that is the horsepower of the fans. They're not strong enough to do the DRPM DT that we need to create the gas structure that we want. So taking this into another measurement, Hurricane Florence, well, obviously, so the mean wind speed here is probably 35 miles an hour. Here we're talking about 75, 80 miles an hour wind. So this is like the higher RPMs, the higher ends of the fan's capabilities. And again, we lose more peaks and valleys here because the fans cannot make what ramp up and down the way that we want. But at the same time, we can create that right gas structure that is required to create the right Ember distribution. So, and we made a proposal to our member companies that if we want to make it even better, we need to replace the fans with like stronger routers. Going back to where we started, so we talked about how we can or how we could create the right gas structure. About the Ember generators, we are working on this. This is an active project. The Ember generators, I guess, started back in 2009, 2010. We used NIST design in the first generation, and then Dr. Steve Coles built on top of that. And 3 generations later, this is what you see here. We have a distribution of embers, which is closer to the real embers, but it's not there. We are still working on it and different designs to create the right ember size. And when we put these two together, well, we can estimate or predict ember accumulation at different areas. This could be a building, this could be a tree, this could be a smaller shrubs. All of those, in my opinion, is the interaction between wind and the inertia of the embers. So talking about finding the right ember accumulation point, there are some other avenues that we also work on, which is machine vision. So this is like a top-down view from the catwalk. Those are the ember generators, and on the top, you see the building. So as the embers get closer to the structure, you see the vortices do their magic and like they disperse the embers, right? So, and you see all of those vortices, and this is like the optical flow. The background is stationary, and then we can do optical flow measurements here to get the ember distribution. I want to look at the embers generators first. So when the embers leave the ember generator, we can count them. How many of them are going to the positive direction? Positive is, well, when they get closer to the building. So on that frame number, positive, and then negative is 0. And then the total, well, it's just a counter, right? So we can count it. But as we get closer to the building, the embers are pushed back by the vortices. And you see those red arrows that if the velocity vector is like the other way away from the building, that's negative. If it moves forward, that's the positive. So, and we can count it, and here is the result. So at about 15 feet from the structure, almost all the embers are going towards the structure. About 5 feet, let's say the average 40% of them are going the other way. So if we want to create a statistical model, or we want to harden the building, we don't need to over-engineer it. We can actually be have more freedom, right? And if we want to quantify it from the modeling perspective, in my opinion, 60% of the embers is what you should be worried about, and not all 100% of them, because they don't hang around. And this gets another layer of complexity when the vortices do their magic is at the corner of the building, which you see it's even worse. So in this case, almost 70% of the embers are do not hang around near the structure. They move away, and obviously because it's at the corner of the building, they go the other way, right? So this is another interesting thing to me. When I analyze the videos, I look at it and I was like, yeah, that was the aha moment for me, that this could be a viable technique. So a critique here is we are projecting a 3D domain into 2D. So we are losing a lot of information. The next step could be taking this into 3D and tracking in 3D domain, which I guess NIST started that, or actually they released their first product maybe last year, very recent. So, and that was like a good news to me. So yeah, we talked about embers. Ember accumulate at a certain part around the structure, ignited, and Dan will talk about this experiment that you see here later on. This is a structure suppression experiment that we work with NIST. We ignite sheds, ADUs, auxiliary dwelling units, and a full structure, and we see the flame behavior. So let me play this video. This is a no wind condition, and we see the flame height and the flame tilt angle from the normal direction. And you see, for the most part, the variation is not that much, right? After 2 minutes, we added wind, a 20 miles an hour wind to the same fire. And, let's see if I can play this video. And here is the result. So the flame height and the flame length, so we're tracking them. And we see the correction factor when we add wind is 2. So if you look at this, so at no wind condition, the flame height, the average is, let's say, I don't know, 18 feet, plus minus a value, that the standard deviation that you see. And the angle is about 0. When we add wind, well, again, it's the correction factor is 2. And this is something that we want to work on to understand it better, because estimating heat release rate and everything with wind is extremely challenging. So I think optical measurements could be very useful here to understand flame behavior and the effects of wind on heat release rate. So with this, Dan will take it back.
Yeah, and hopefully my connection's a little bit better here. Thanks, Faraz. And so, you know, with that as context, you know, to get to some of the, where Faraz talked about the hazard side of this, talk a little bit about some of the previous and ongoing work that we're doing right now to, again, understand how the natural hazard, the wind, and the thermal impact from wildland fire, in this case, like the flame and the embers, can impact buildings. And in our organization's name, business and home safety, you know, we can kind of lump those commercial structures, businesses, and homes, residential, into a category of buildings. And so what we'll talk about here is looking at you know, single family homes. So these are going to be residential, but I think the vulnerability aspect, which I'll describe, can be generalized also to commercial, and thinking about the building as a system of components. So now I'm going to highlight 2 of those systems here. One will be the through roof vents, and the second will be the decks, and where we've looked at specific vulnerabilities of those components, like here with the vents. We know those embers that Faraz was talking about. Vents are intended to have a pathway for air to communicate in and out of, in this case, the attic. You need that ventilation for moisture control. but it also creates a pathway for embers to get inside. We know some kind of straightforward ways of not preventing but reducing embers from getting into the attic, and that's one of the primary concerns we have. Embers get into the attic, they can fall down onto the ground and ignite something. We can use something as simple essentially as a filter or metal mesh screen, and we looked at different sizes, 1/4 inch, 1/8 inch, and 16th inch. And unsurprisingly, the finer the mesh, the smaller the opening, the smaller the ember size it allows through, or the better the filter is. Now, you still get some embers inside, but the end result is a smaller ember, as Faraz was talking about, that mass as you think about it as momentum. Also thinking about it as essentially energy. Smaller embers are likely to have less thermal energy or capacity and are less likely to ignite something. So vents are important, but we can mitigate them. We can use that mesh screen not to prevent embers from getting there, but to prevent them from getting in and likely ignite, or reduce them from getting in and igniting something. Another component that we look at is the decks. Now, decks aren't on every structure and are probably more common on residential than commercial. But decks are a bit different than vents, and this is a sped up video. On the left-hand side, you actually have a wood deck with a metal substructure, and on the right-hand side, you have that same redwood walking surface, but a wood structural support system. And what we're trying to show here is that the material of the component, a deck is not just a deck. It's what the deck is made of. So not only is a building a series of components, the roof, the vents, the eave, attachments like decks and pergolas, it's not just a series of those components. Each of those components can be assemblies in and of themselves. And so we can really dive deep into understanding the top surface of decks and their vulnerability. But really, we believe at IBHS it's important to consider the building as a system. And so, Faraz, if you're able to start this video, this is a demonstration, and what we have here is essentially a duplex side by side. We're using the same Ember generators that Faraz was just talking about and characterizing. And in this duplex, we're trying to show two homes as a system. On the left-hand side, where you see the flames, we have combustible mulch in that first 5 feet, which we know is really important. We also have combustible siding, single pane window, and open eaves. On the right-hand side, which is experiencing the same ember exposure, we have rock mulch, or non-combustible, in that first 5 feet. We have non-combustible siding, multi-pane windowed, and enclosed eaves. And so this is just a 60 seconds from the clip of the demonstration. You can see the full demonstration online. This is about 7 minutes after the start to give a sense for when those embers were able to ignite. But we see here in under a minute, the fire can pretty rapidly spread from that ignition in the mulch up through the siding. It breaks the window, so it can enter the home through the window. It gets up into the open eaves, and there is ventilation into the attic in that gable end side. And so we could see, if we had prevented the ignition in that first 5 feet, which is something that we talk strongly about, that 5 feet of home ignition zone and needing to be ember resistant, that's important. But we also need to consider, okay, well, even if we had a perfect 5 feet, if we did ignite the siding and the siding was combustible, it can carry fire spread up. And then you have to think about the eave area, and then you have to think about penetrations through that window. So, I think one of the important things to take away from the work that we've done in thinking about building vulnerability to all hazards, but particularly wildfire, is acknowledging them that they're not just roofs. Class A roofs are important, but a Class A roof is not the end all be all. That's not the only part of the building that's going to be exposed to the fire hazard. So. With that, I'll move along to some of the other ongoing research. This has generally been the past. You see some familiar faces here, and I see on the participant list. This is from some 2016 testing with you all, the Missoula lab, our Forest Service collaborators, and we're looking at fire spread through pine shrub beds. And so one of the notable things here, for those of you that have been to or know the Missoula lab, look at the wind speed. So 17.5 miles an hour is near, not at the lowest, but near the lower end of the wind speeds that we looked at. Faraz talked about doing wind speeds up to 70, 100 plus miles an hour. Those are very common for hurricanes, but for wildfire at those wind speeds, you're essentially blowing it out. And so one of the things that we've been working on over the past couple of years, in the same way that we try to understand the hazards of hurricanes, is trying to understand the wildland fire hazard. And this is an area where we really see potential and have got a lot of benefit from thus far and look forward to in the future is using the facility and our capabilities to understand this wildfire hazard. So this is just fire spread in a continuous fuel bed. Earlier this year, several months ago, some of you were out at the facility. We were looking at fire spread through discontinuous fuels, and so that's increasing our understanding there fundamentally, and then practically to develop tools. And then ultimately, it helps us IBHS again. If we're focused on the homes and the buildings that can be impacted by the hazard, we need to understand more. We need to understand the fundamentals that Faraz was talking about and what's going on in that hazard to then focus in and see how it impacts the homes and communities. Another ongoing project that Faraz showed is burning sheds. This is an aerial. In those burning sheds, you saw just a shed there in the center of the frame. This was not during a fire test, but we'll eventually get to this point, and this gives you a scope of what we're doing here. What we're trying to do is better understand the separation distance between structures, and really what that needs to be, or rather at what separation distance is, how common or the potential for this burning shed with the wind at its back blowing those flames, as Faraz showed, up to 40 feet to impact that target structure. This is your home in a suburban community. How far do those sheds need to be away? I think we can pretty commonly understand the larger the shed, the more flame volume, the more flame potential, the more fuel loading in it, the farther that flame is going to reach. And so we're looking at different size sheds from, very small, think closet size things that you can have right up against your home, to, more kind of, typical where you'd have your lawnmower 8x8. And this here shown is a very large. And so this is a really big project. Faraz mentioned one of our collaborators, NIST, but also we're working with the U.S. Forest Service out of your Pacific Northwest lab, Ruddy Mel. And one of the parts of this project is to not just do the experimental work. It's important and to take those measurements, but Ruddy is facilitating in the experimental work with the computational side of things. And as Faraz mentioned, we're starting with sheds, and we'll gradually get up to larger source structures, to ADUs, 600 square feet, single family dwellings in the 1,200 to 1,800 square foot size. We can burn a lot of sheds, and that's one thing that we're good at. It's really exciting. But if we go back to that, that core value of real world impact, we don't want to have to test, or we don't want to need to be in a position that we need to test every possible configuration. So that, again, this is an area where, I know Natalie wasn't able to be with us today, but she was the one that invited us to speak here, because we really want to leverage those of you that have modeling backgrounds and do some of the simulation work to both help inform, but also build upon the experimental work that we're doing. So with that, I will go into one slide here. I think that this is something that we just want to plug to make you all aware of. I talked about some of the previous research that we had done on individual components, but acknowledging the home as a system. One of the things our members, the insurance industry, and generally people that live in wildfire prone areas or where their homes and communities are vulnerable to wildfire, are asking for, well, how do I make my home wildfire resistant? And I think, research over the past few decades include from Jack Cohen at the Forest Service, our predecessor, Steve Quarles, and many others. I think we have a general sense for the important things, the components of the building that are vulnerable and the best things that you can do to harden them against that. One of the challenge then becomes is, all right, I know how to build new, maybe what I would consider the most wildfire resistant structure, but what about the millions of homes that are existing in communities right now that have either been already posed or exposed to, or likely will in the near future? And so IBHS is working on what we're calling our Wildfire Prepared Home program. It's not the same, but is in some ways similar to our Fortified program, which is a designation program that the insurance industry uses to acknowledge structures that are built to be more resilient to the hazard. And so the Fortified program builds on the science that we have from hurricane research and high wind research to have a continuous load path of a structure, a fortified roof that's going to resist those shingles coming off, and if they do, water from getting inside, which can be a big damage factor. And Wildfire Prepared Homes builds on that same methodology to think about how do we designate structures that are more prepared or prepared enough, or as prepared as we that are more prepared for a wildfire. And so, Faraz, if you can give me a click to talk about some of the components here. We know that the roof is important. So Class A fire rated roof, this is something that, again, we get questions all the time. There are so many things I need to do my house. I know the roof is important, so I should replace my roof with a Class A roof, which I would agree with is true. But, I think, this idea or, this worst case scenario that we have so many wood shingle roofs out there, that is a probably worst case scenario. But with some of our partners, we know that in California, which is where we're primarily focusing, rolling out wildfire prepared home initially, more than 90% of the existing homes already have a Class A roof. And this is based on the reality that most homes, the majority of homes, have a asphalt shingle, and an asphalt shingle roof is already a Class A. So that's a big important thing, but hopefully it won't be too much lift because we believe most homes will already have a Class A roof covering. Other building features like the vents that we talked about, we know embers are going to get there. We need to resist them from getting inside the structure and igniting something there, as well as little features like at the base of the wall. Go back one, Faraz. At the base of the wall where the embers accumulate, where Faraz was talking about. We have a lot of other things. We'd love to see non-combustible siding throughout, but particularly in that lower 6 inches where those piles are going to accumulate, making sure that's ember resistant. And then other things around the structure. I think many people are familiar with the concept of defensible space or near building landscaping. So we talk about, again, that first 5 feet being critically important. We talk about decks, that deck research that we had showed looking at the support structure of either a common wood support structure or a metal support structure. That's really most vulnerable to that underdeck fire scenario. So if you can reduce the likelihood of that underdeck fire scenario, maybe your more vulnerable, less than ideal wood substructure will fare better, but that requires maintenance. That requires keeping that clear. And if you can, actually enclosing it so that way additional debris doesn't accumulate there. And then again, other, defensible space things like, trimming trees back and where you do have vegetation outside of that 5-foot zone, clustering it and spacing it so that it doesn't provide a continuous path. Again, building on some of that discontinuity of fuel research that we're working on so it doesn't spread up to the structure. So just so people are aware, again, I know, Jack Cohen, who's retired now, did a lot of the home ignition zone stuff, and I'm not sure if other people on the call are looking at that, but that's very much an area of the research that we're looking at and wanted to make you all aware of that if that's something that you had thoughts on or wanted to learn more about. And then as a final closing thing here to talk some about what we as an organization do, not just in the research and the research communication space, though that's very important. Again, building on that real world impact phrase, we do participate in, other arenas and, I think what's generally known as the policy arena. So in codes and standards, we participate in standards development through ASTM and UL and others. We participate in development of model codes, including at the ICC and NFPA, as well as state codes. And again, I think, California is a gleaming example, is really leading the pack in this space and their state building code that addresses exterior wildfire exposures. But also, it's not just, what we put the words on the page, it's coordination and collaboration. We talked about the collaborative research projects that we have with the Forest Service and others. Looking at state agencies and national and international partners. So hopefully that's a good segue as we're finishing up the presentation here to get into some good discussion with you all for what we've done in the past and what we can answer and provide more information on. If it's not clear, Faraz is probably the most technical of the two of us, but together in tandem, we work very heavily in this space, but also what we can and will be doing in the future and how we can best leverage the strengths and capabilities of IBHS with those that you all have. So with that, I think that's the end. Yeah, we put our contact information here. We're both pretty active in the social media space, Twitter, but are always open to, some exchanges of emails or a quick meeting to chat. So put that contact information up here as well. And I'll just say thank you all for the invitation to participate and hand it over to Faraz if you have any other closing thoughts.
Yep, thank you, Dan. Echoing Dan, we are really interested in participating with you all on the modeling, on the experiment design. We have a good facility that I think collaborating with other researchers, we can have a more impactful research.
All right, thank you, gentlemen. Appreciate that. If anybody in the audience has questions, go ahead and type them into the chat box, and I can read them off. While we're waiting, though, so you showed some really impressive experiments. I'm just curious, how do you go about synthesizing the results into something the insurance industry can use?
Good question. I'll take a stab at it, but I think my high level answer is there's no one way to do it. You talked about our different, member constituents from the insurance industry, primary carriers, reinsurance, and there's companies that support this kind of world of insurance. And so, for example, the cat modelers, they're the ones of the world that are really data heavy, and they want the nuance, the detail, and they want the statistical side of it. But the carriers, they're kind of more looking for what do I tell my policyholder? So we're really going to have to deal with the range of it. And also it depends on, what we were trying to achieve with that. So I don't think that there's any one size fits all. That's an important part of the work that we do, is trying to think about, who's the audience, what are their questions, and how do we package it in a way for them? And just to kind of give a hat tip to our colleagues that work in that space, if we're on the ground doing the research, they're helping us have those conversations and package it that way. But data sets, reports, infographics, kind of the full range of it. Yeah, it's all part of the communication of the science.
Carrie Yedinak asks, thank you, Dan and Faraz, for the presentation. How much interest does IBHS have in investigating structure-generated embers in adjacent structure ignition?
Yeah, we have done research like that before in a smaller scale, not a full scale. We are definitely interested in that. I guess there are different ways to look at this. Looking at particle tracking type of research, or looking basically optical measurements, looking at physical measurements, laying down water pans, cutting sheets, or different type of research. Personally, I am more interested into scaling up things. So we can burn one structure, two structures at IBHS and look at the physical measurements, right? But how can we take that into a neighborhood? That would be more interesting to me, to look at bigger scale fires and basically extrapolating from measurements. So maybe if we can model what we have in smaller scale, in the bigger scale, that would be very interesting to me. Dan?
Yeah, and I just shared the JFSP report for us, which I think you were alluding to. So yeah, really good question, Kara. We looked at ember generation or production from burning things, and you think about that kind of life cycle of the embers. So for that JFSP project, we looked at embers generated from vegetative fuels, and we looked at a fuel including chaparral and blue stem grass and a couple other vegetative, but also structural fuels. And so we had some mock-up of a wall assembly or a roof assembly or a fence assembly. I think the general takeaway is that structural fuels generate larger embers, which have maybe more ignition potential. But as Faraz mentioned, that as a kind of general takeaway is helpful in thinking that larger embers are more likely to ignite something. Those admittedly for the JFSP project were only kind of segments of a wall or segments of a fence. And so they're helpful to give us some insight, but maybe not the full picture. And I think to explicitly answer your question, Kara, we are interested in that. And so thanks for bringing it up, and please reach out if we didn't answer it enough here to follow up.
Here's a message from Greg. The research you all are doing on ignition from embers is great. I'm curious, with respect to the different zones in the home ignition zone, how much are those based on embers versus convective heat versus radiant heat? The zones of 0 to 5, 5 to 30, and 30 to 100 feet.
So Greg, very good question. I try to answer that. Dan helped me here. I don't think there is a solid statistic for that. There are some Australian studies which you might have seen that they say 90% of the home ignitions are caused by embers. Well, I think like going through reading between the lines and how they describe this, I feel like if embers causes small flames and the small flames touch the wall and then siding of the building and then the building ignites, they include that into embers. I don't know if I agree with that, that if I cannot distinguish that in my mind, that if it's like a small embers, small flames or big flames caused by embers or not. But I can say the majority of the damage is caused by embers. And that would be, in my opinion, 0 to 5 feet, because that's where the wind pattern changes as it gets closer to the structure. So this stagnation point basically of the flow. And then that causes ember accumulation.
Yeah, I think Faraz, that work on the near building zone that we did a couple of years ago, and I'll probably post to that report and send in the chat here. I think, Greg, I think that's kind of the summary answer to the question. That very near building zone, about 5 feet, we think is really most important when we think about direct flame contact, for the reasons that Faraz just described. In the wind, you create that stagnation zone. And at higher winds and closer flames, you actually blow the flame away. So, that near building zone, want to harden against embers, because if you get flames in there, then they'll just touch it. But further out, generally the flames don't touch it. Now we're trying to enter that with structure separation of the sheds. We've only burned type vegetation size fuel, so that might change. But I think in general, I would also say that, the different home ignition zones, the kind of binning of them, I think that's one of the things that we're trying to better understand ourselves. And I think that this is an area where we would love to lean on you folks with a more ecological background, because in that first 5 feet, we can talk about, the vegetations and the need to be ember resistant. There are also the structural fuels in there. But I think generally when I think about houses and see houses in that 5 to 30 and 3100, it's more commonly vegetative fuels than it is structural fuels. And so thinking about the ignition in those zones and then fire potentially spreading to the structure, I think really needs to include the ecological aspect of it. So in short, I think direct ember ignitions are, have a factor, but maybe are not the number one factor. I think the bigger attribution of ember ignitions are because embers ignite some fuel, whether it be vegetative or structural, close to the home, and the flames from that, radiative or convective direct flame contact, are what ignite the structure. But we got to kind of think about the fuels in those different ranges and the conditions that would cause the burning thing for the direct flame contact or the radiant heat transfer.
Okay. Jeff Marshall asks, what size and mass range of embers are being produced by the generators? Have you looked at large surface area particles like ponderosa pine bark or manzanita leaves?
So Greg, the link that Dan sent, the JFSP study on page, what is it? 30, there is a graph that compares with 95% confidence interval. What are the different combinations of the studies out there? This is based on the 2019 study, so it's like not very recent. If you look at that, you see the NIST's first generation of ember generators is just a dot. And then their second generation, it's basically 0.01 gram. So it's very, very small embers. IBHS ember generation is not in this plot, but I would say that's similar. That's bigger than what NIST does, but it's not even close to what it should be, and that's what we're working on right now. About the vegetative embers. I think it's a challenge at the current technology that we have to create those embers, because they burn out. The surface to mass ratio is very large, and as soon as we ignite it, it becomes a pile of ash. So we cannot give that like the flight pattern that we want. So that's just the area to study for us, and we're very interested into working on ember generators to make them, to create more realistic embers, and we need your help on that.
Yeah, and Faraz, you mentioned the JFSP report that you just talked about into the, I think it was Greg. I put a link in to what we called the near building non-combustible zone report, which talked about, you know, why we kind of really champion, other people have saying it, but, you know, continue to champion the 5 foot, and it looks at the building orientation and the wind speed and that eddy effect that Faraz was talking about. So if you're interested, we're posted there.
Okay, great. If there's any more questions, go ahead and type them up. Meanwhile, I want to give a little announcement. Next week is our first panel discussion on climate, and this will be part 1 of 2, the state of climate science. And we have Dr. Jinglei Huang, Dr. Phil Moat, and Dr. Isla Simpson, and they'll be holding a panel discussion. They'll start out with a little talk, opening remarks, and then they'll hand it over to the audience for questions. This is a special session. It'll be 90 minutes long, and we hope you'll tune in. Well, if there's no other questions, I guess we can wrap things up. Faraz and Dan, we sure appreciate you giving a presentation today. Thank you very much. And I'll be emailing you later to get your mailing address so we can send you a little gift for our appreciation. So if there are no other questions, I think we can wrap it up. Thanks again, guys. Appreciate it.